Question 11. Figure 2 shows a sketch of part of the curve with equation y is equal to ln x all squared, where x is greater than 0. The finite region R, shown shaded in figure 2, is bound by the curve, the line with equation x equals 2 and the line with equation x equals 4. The table below shows corresponding values of x and y with the values of y given to 4 decimal places. Part A, use the trapezium rule with all the values of y in the table to obtain an estimate for the area of R, giving your answer to 3 significant figures. So let's look in our formula booklet where we will find the trapezium rule. So we have an area under a curve, and we know an area under a curve to be an integral of that equation. So in order to use our trapezium rule, we need our a value of 2, our b value of 4, our y values, starting with y 0, we have the following in the table. Our h is equal to b minus a over n. We are going up to y4, so n is 4, which gives us a height of a half. So we have our integral of ln x squared, which is our y, between the values of 2 and 4, our a and b, is approximately equal to a half times our h, with our y0 and y4 plus 2 lots of our y's in between. Being very careful when entering this onto our calculator gives us an answer 2.408 and so on, which is 2.41 to 3 significant figures. Part B, use algebraic integration to find the exact area of R, giving your answer in the form y is equal to a ln 2 all squared plus b ln 2 plus c, where a, b and c are integers to be found. Well, for this question, again looking in our formula booklet, we are going to be using our integration by parts. We are starting with our integral of ln x squared. Now this is the same as ln x all squared times 1. So using our integration by parts formula, if we let u equal ln x and v dash dv by dx equal 1, we can integrate 1 to just get x, and we can differentiate ln x squared to get 2 lots of ln x, multiplying by the power, subtracting the power by 1, and then multiplying by the derivative of ln x, which is 1 over x. So that's using the chain rule. Simplified, this gives us a du by dx value of 2 over x ln x. Substituting those back into our integration by parts formula gives us that the integral of ln x squared dx is equal to x ln x all squared minus the integral of 2 ln x dx. We can take the 2 out of this integration here to give us x ln x all squared minus 2 of the lots of the integral of ln x. Again, to integrate ln x, we are going to do something very similar as we did with ln x squared. We're going to let u equal ln x, and we're going to let dv by dx, v dash, equal 1. The derivative of v can be integrated to get x. U of ln x, we know to differentiate ln x, it's 1 over x. Putting them back into this integration, using the integration by parts formula, we've got that our integral of ln x all squared dx is equal to x ln x squared minus 2 lots of our integral of ln x, which is x ln x minus the integral of 1 dx. The integral of 1 dx is just x plus c, which is some constant. Expanding this bracket, we've got our final integral of ln x squared dx is equal to x ln x all squared minus 2x ln x plus 2x plus our constant now called a. So starting from here, so this is the integral of ln x all squared. We are looking for the definite integral between the values of 2 and 4. So we can ignore our constant now and just say that this integral is between 4 and 2. That is substituting 4 into this expression and then subtracting, substituting 2. It is a good idea to work these out without the use of a calculator, as the calculator will jump to giving you decimal answers. Ln 4 should be noted is the same as ln 2 squared, which is the same as 2 ln 2. So this is 2 ln 2 all squared. 8 times 2 ln 2 is 16 ln 2 plus 8. And then dealing with the sign change here, because it's minus these values. This gives us 16 ln 2 all squared minus 16 ln 2 plus 8 minus 2 ln 2 all squared plus 4 ln 2 minus 4. Simplifying that, 14 ln 2 all squared minus 12 ln 2 plus 4. And this is in the form that we require.